Alrighty, let's go ahead and wrap up chapter 12 here in part 4, talking about further radical substitution reactions dealing with allylic and benzylic hydrogens. So kind of tying back into some of the material from chapter 8. Okay. Now, just like an allylic carbocation, an allylic radical has two resonance contributors, right? Think about this as being a carbocation here. We would have drawn a resonance contributor, and our radical does the same thing, right? Dealing with a homolytic cleavage of this pi bond to reestablish a pi bond here and move the radical over onto this carbon. Okay. Two resonance contributors for an allylic radical, and we have the resonance contributors, 5 of them, for a benzylic radical as well, moving them around the exact same way as we would have the carbocation, right? So you can think about how those work for practice, but the big takeaway is the stability at the end of the day, right? We know the more resonance contributors something has, the more stable it is. And what that means for us is just like carbocations, our benzyl radicals and our allyl radicals are more stable than everything else, including tertiary. Right? So this chart should look familiar. It's the same exact thing we had for carbocations now for radicals. Okay? Our benzyl and our allyl radicals are more stable due to electron delocalization in those resonance contributors, okay, followed by tertiary, then secondary, then primary. Okay, vinyl is bad because of that electron density being right next to it in the pi bond, and methyl is the worst. Okay. So what does that mean for us in terms of reactions? Well, the more stable the radical, okay, with our benzyl and our allyl radicals, the faster that it can be formed, the more stable these radicals are. So that means that if we're doing radical reactions, okay, radical substitution reactions specifically, if we're replacing a hydrogen, the hydrogen on the allyl or benzyl position are preferred. Okay? So even though we have hydrogens right here that are more likely in terms of probability, we're going to get the benzylic substituted product here, okay, dealing with adding chlorine or bromine in a radical reaction. It's going to preferentially go to the benzyl position or the allyl position specifically. Okay. And a big takeaway here is a new reagent, a big takeaway from chapter 12 in this video specifically. This video covers a lot of slides, but right, make sure you got the big takeaways. That is, we have a reagent that's specifically used to brominate in the allylic position. Okay, know this reagent. Know NBS, N-Bromosuccinimide. Okay? Know that what NBS does, right? Recognize it. Okay? Just like MCPBA from earlier chapters, NBS is another really important reactant, right? Really common. And we use it because it's more environmentally friendly than using bromine, and we can do it at lower concentrations. And the other advantage is if we were adding Br2, we would have a competing reaction, right? Adding to this alkene, same thing with HBr, right? We know how those react with a pi bond there. So if we're trying to brominate in the allyl position specifically, right here or here, these are identical allyl carbons, thinking about it in 3D, we use NBS, okay, with lighter heat and peroxide. So know that combination. Have NBS jotted down, recognize it. Okay? It dishes the bromine from NBS, puts it in the allyl position, and you get succinimide as a byproduct. Okay? Here's what the mechanism looks like. Okay? The reaction begins with a homolytic cleavage of the NBr bond in NBS. Okay? That generates the bromine radical right here. So this previous bond right here, we have a homolytic bond cleavage that gives us my bromine radical. And think about that as the initiation step. Then we have a propagation here with that bromine radical and these two allyl radical resonance contributors. Okay? Then we have a second propagation step coming from Br2, right? That homolytic bond cleavage, thinking about that with heat or light. Okay. Now, the bromine that's thinking about here, right, in the second propagation comes from an ionic reaction here between NBS and HBr. That gives me my Br2 here. Okay. And at the end of the day, even though we have two resonance contributors, I alluded to this previously, we just get one product. Thinking about this thing in 3D, that's an identical product. Okay. So know NBS and know how it works, right? This down here is new, this up top is not. You know bromine radicals, you can predict the propagation knowing the allyl position is preferred. Okay. Now, if you have a situation where the two resonance contributors are not symmetrical, as we just saw, right, then you would get two products, because we have two different radicals that can go into the second propagation, right? One putting the bromine with the methyl group, one putting the bromine group 2 carbons away. So be on the lookout for that as well. Again, difficulty in selectivity with radical reactions. Yep. And at the end of the day, be on the lookout for bromine. It can do both addition reactions and substitution reactions. Okay? We can have bromine add to the double bond, as we see on the top. We can also have the bromine radical pull off an allylic hydrogen. Okay? So the concentrations are important, because addition to the double bond, what we have going on up top here, is faster, okay? Because it just requires breaking a bond there. Pi bond's weaker than a sigma bond, so that's a piece of cake, right? So that's going to be faster, okay? But if there's no hydrogen available, the reaction goes back, and then you get the substitution product. And so we're jumping back and forth here, going down to the bottom, getting the substitution product at the end of the day. Okay, concentrations are significant if you want to control that. Okay, if you use NBS, right, N-Bromosuccinimide, there's too little HBr present to complete the addition reaction. Okay, after the bromine radical is added to the double bond. Okay, so we're taking advantage of that. We don't have the HBr present. It jumps back because it's a reversible reaction, and then the substitution becomes the major reaction. Okay, so NBS pulls off the allylic hydrogen, whereas if you wanted to add to the double bond, right, if you wanted to do this reaction at the end of the day, you can, but that's from our previous video, video 3, using HBr and peroxide together. Okay, so if you want to do an allyl substitution, you use NBS. If you wanted to brominate in the allyl position, doing an addition reaction, right, then you would use HBr with the peroxide effect. Okay. Lots of information there for NBS, right? That's largely explaining how it works. Jumping back a couple slides here. My big takeaway is if you see, right, a pi bond and NBS together, plus heat or light and peroxide, got to be everything together, know to put a bromine, one of them, in the allyl position. That's a huge takeaway from this video. Okay, so that's 12.9. In this video, we also have 12.10. Right, which has a lot of synthetic examples from 9, 10, and 12 all together. And I'm really going to recommend you take some time and look through all of these, because it's an excellent way to review and study for your tests, right? Here we've got an ether and an HI from chapter 10 coming together, then the oxidation of an alcohol, also from chapter 10. Right? Another synthesis. Here we see we're using bromine and light, so that's a radical reaction from chapter 12, but then we're doing an elimination reaction from chapter 9. Okay? Then another NBS reaction from chapter 12, and another elimination, right? Terbutoxide here, and heat to favor the elimination. 4 reactions. As you go through and you look at these, make sure you are actually understanding what's happening in each step. Okay? The syntheses could be difficult to put all 4 steps together, but understand what's happening. That's what you want to do when you're going through 1210. Okay? Here we see it again. Radical reaction, elimination. Ooh, there's a bromine plus dichloromethane. And that's an old reaction, I think, from chapter 6. Okay, so tying lots of ideas together with these synthetic examples. Take some time, to look through chapter 10, or sorry, section 10. Right, that's a really good place to spend some time on your own. We could finish here by briefly discussing radical reactions in biological systems in the environment, which is kind of weird to think about because we've said that radical reactions require heat or light to initiate, and propagation can easily get out of control. So how do we see these in biological systems, right, in the human body included? Well, radicals can be formed by the interaction of organic molecules, right, with metal ions. We can see organometallics. Right? Here we've got a hydrocarbon, right, not great to have in the body, convert it to an alcohol, easier to excrete and less toxic. Okay? This is the type of reaction we see in cytochrome P450, where we see going from iron 5 to 4 to 3, right, to deal with our radical intermediates, right, converting nonpolar to polar to deal with excretion. Oxidation of fats and oils, that's a radical reaction as well. Okay? That's why things like olive oil, right, over time, that'll go bad. It's exposed to oxygen. It occurs via a radical mechanism. Okay? And you've heard of antioxidants in the body, all right? And what antioxidants are really radical inhibitors. They prevent oxidation by radicals, hence antioxidant. That's why you want those in your body, right? Because that same process that we just saw here happening to fats can happen to cell membranes, right? You don't want this. This is what happens when you get old, right? Destruction of some of those cell membranes and aging. Okay? So we have antioxidants to deal with reactive radicals, vitamin C and vitamin E. Okay? That's a lot of their role in the human body as antioxidants. Vitamin C better in aqueous systems, whereas vitamin E is fat soluble, better in the fatty systems. Same type of chemistry in food preservatives, for example. And none of this will be on the test, right? This is all biochem. Everything after slide 64 here. None of this would be explicitly tested. It's more just of an FYI that it exists. Okay. Ozone formation. Right? We know ozone's good in the stratosphere, right? 12 miles up, because it absorbs harmful UV light, right? But it's not good at ground level due to ailments with the heart and lungs. Okay? Major constituent of smog. So we don't want it at ground level. We want it up higher. Ozone holes being, right, in 2021 now, it's being restored. But what led to that hole in the ozone layer to begin with? Why did that happen? You probably know the fact that it was due to chlorofluorocarbons, right, CFCs, which were used in HVAC systems, right, heating, ventilation, air conditioning. It was used in HVAC, it was used in aerosols, right, those propellants, because of a number of advantages for CFCs, right? And there are a variety, this isn't the only one. They're odorless, they're non-toxic, they're non-flammable, they're chemically inert. So they were really good before we figured out they were destroying the ozone layer. And how is that happening, right? We saw right here that these CFCs can produce chlorine radicals, and those chlorine radicals love reacting with ozone. One chlorine radical, as you see on the bottom there, can destroy 100,000 ozone molecules because of this insane rate of propagation, right? Taking those ozones and converting them to O2, just radical chain reaction, propagation, propagation, propagation. There's no easy termination there, okay? So, which is why CFCs are largely banned nowadays. Yep. But on that happy note, that wraps up chapter 12. Big takeaway here, know what NBS is, the fact that it brominates in the allylic position, okay? NBS, heater, light, and peroxide all together. And then you look over 1210 to review chapters 9, 10, 12, a lot of the material to date. Really great area to review right there.